is degrading. I think I got cold, so but hopefully it lasts for next hour or so. Before I start, I'd really like to thank you, George and Miller, and whoever involved for organizing this great event. It's really a big pleasure to be here. In terms of topics I'm going to cover in next hour or so, First I'll spend some time doing a general introduction to crystallographic structure refinement, and then I will proceed into practical implementation of the theory that I will show in terms of structure refinement tools in Phenix, namely reciprocal space refinement tool in Phenix called Phenix.refine. And then I will touch on real space refinement tools tailored specifically to low resolution X-ray and cryo-EM maps. Also like to mention that most of these talks and relevant publications are available online. So if you go to Phenix web page, it's, I don't know if you can see it. Oh yeah, you do see it. It's available here. So there are two links, publications and presentations. And in presentations, you'll find PDFs with talks. If something that I'll show today isn't there, then just let me know and I'll put it there. And yes, just to mention, I'm working as part of Paul's group in Berkeley. Spent about 12 years of my life working on structure refinement in Phenix. And with this, I proceed to introduction to structure refinement. And by the way, yes, I repeat, it's meant to be very informal. If anything isn't clear, just stop me and ask questions. It's very, very welcome. So, structure refinement. Well, this is the typical, very sketchy outline of typical crystallographic structure determination pipeline. You get purified sample, you get crystals, you get experimental data, you solve phase problem and get your model. Then you basically have a step called refinement, where you go back and forth between model building and improvement, which is refinement. And that is actually tightly integrated with structure validation, so you don't want to overlook errors and carry them on entire process of structure solution. And then finally, publish a structure. So in this paradigm, refinement is just one piece of this chain. And what is refinement? In general, refinement, structure refinement is optimization problem, which particularly in crystallographic case is solved iteratively, which is outlined here. So you have initial model, which is some initial A model, maybe poor. You calculate structure factors from this model. You match the structure factors against some available experimental data and use some scoring function to evaluate the match. We iterated several times, and hopefully in the end we get an improved model. So since structure refinement is an optimization problem, there are three fundamental things that are typical, that are common to definition of optimization problems. So one is we need to define what is model and what are the parameters describing this model. And in our case, that's going to be atoms in unit cell and something else. Then we need to define the structure. We need to define a scoring function that is going to bring model descriptors, parameters, to experimental data in some way. And finally, we need to have a tool that will change model parameters in such a way that the model fits the data as good as possible. And also, the model needs to comply with some a priori knowledge. So, and in the next few slides, we'll go through these 3 steps very briefly. So, model parameters, what are those? So, this is very schematic representation of a unit cell. You have a molecule, macromolecule here, and lakes of bulk solvent. So these are not voids, but actual bulk solvent, which has, and in certain approximation, it has a constant electron density. So in turn, that lets us postulate that in terms of model parameters, we have 2 types. Atomic model parameters, which are parameters of atoms, and non-atomic model parameters that describe everything else. And in turn, in terms of structure factors, we can, in this paradigm again, we can define the total model structure factor as a contribution arising from these 2 types of models we use. One is contribution from atoms, F-calc, and the other contribution from bulk solvent structure factors. And we may have a way to account for anisotropy and various scalings here. And this is actually structure factors that go to all the calculations down the road, such as R factors, maps, refinement targets, and so on. So it's a typical misconception that people think of using F-calc, calculated from atomic model, to calculate all these metrics that we typically use. In fact, the total model structure factor is a little bit more complex, and it's pretty much what I have here. Just to illustrate the contribution from bulk solvent, may be instructive to look. And indeed, an instructive way to look at it is to plot R factor across as function of resolution. So what we have here, we have R factor without and with bulk solvent contribution accounted in total model structure factor. And what we can learn from this plot is that bulk solvent contributions start showing up at approximately 3.54 angstrom resolution and lower. And as you lower you go, then the bigger contribution from bulk solvent you get. In terms of atomic model parameters, well, we represent atomic models pretty much like this. And what really diffraction experiment conveys to us is an average image of the molecule. It's space and time average. Space average because we have average across multiple unit cells of molecules, swarms of molecules, and time average because atoms are in constant vibrations. So in terms of parameters, this translates into what we typically see in protein data bank, structures in protein data bank records, this atom and another U records. So basically we have a position of atoms that describe coordinates of atoms in a unit cell. We have occupancy factor, which describes large-scale disorder that is larger than can be modeled within harmonic approximation using B factors. So basically occupancy models something that cannot be modeled with a B factor. And B factors, isotropic B factors or anisotropic B factors if TLS model is used or if high resolution data is available to refine individual anisotropic B factors. So, and just to make it clear, the way it gets into the calculations. So again, we have a total model structure factor here, and this is the structure factor formula taken from any textbook. Everybody knows that. Yes?
So what does the second line mean? I mean, anisotropy, that's
Which
8,443. What are those?
These are?
Yeah.
These are anisotropic displacement parameters or anisotropic B factors. They describe harmonic vibration of atoms that undergo that vibration anisotropically. Yes.
Those are a measure of the principal axis of an ellipse rather than a spherical.
So what does it tell you? I mean,
it tells you directionality of atomic vibrations. So instead of a sphere
right.
of a harmonic model, an isotropic model tells you directionality of atomic vibrations.
It's the elements of the tensor that
Oh.
describes that.
Can you give some sense out of the numbers? I mean, quick.
Oh, it's a
It's difficult to look at directly.
yeah. I mean, you can take an isotropic structure, any anisotropic structure from PDB and load it in PyMol, and you can visualize actual ellipsoids associated with each anisotropic record. Could does that
Looking at
too.
those raw numbers is very hard to.
Okay.
It's basically elements of an isotropic matrix which is symmetric, so we have only part of these elements because the matrix is symmetric. So, and this is the way how these parameters go into structure factor formula, which is again taken from any standard textbooks that I'm sure everybody is aware of. That's a sum over atoms. Here we have occupancy, scattering type. In this case, that's the carbon. That's the isotropic B factor. In case of an isotropic B factor, it will be a little bit more complicated formula. And here we have coordinates. Just so you have an understanding of how these numbers get translated into structure factors. Okay, speaking of atomic parameterizations, I'm sure whoever tried to refine structure faced dilemmas about how I parameterize my structure, whether I refine occupancies or not, whether I refine isotropic or anisotropic B factors, use TLS or something else, rigid body or individual coordinates, and so on, so on, and so on. So the choice for model parameterization is defined by two factors. Current model quality is number one, and data quality is number two. Obviously, you wouldn't refine anisotropic B factors at 3-angstroms resolution. Or even if you have 1-angstrom resolution data set, but model is very bad, say 40 R factors, 40%, then you probably don't want to start with refining anisotropic B factors. You refine isotropic first and then switch to anisotropic. So atomic model parameterization is largely depends on two factors, data quality and current model quality. Okay, moving on, scoring function. So what is scoring function? Splitting, that's the function that brings atomic model parameters, that relates atomic model parameters to our measured data. And in case of crystallography, your data are FOPS or IOPS intensities. In case of CryoEM, your data is MAP, and so on. So it can be formulated in more general terms. And so typically, this is a very schematic illustration of what goes into our scoring or goal or refinement or target function. So we have structure factors calculated from model, which contains atomic and non-atomic model parameters. Here we have observed structure factors, so we have X-ray or data term, and we have some restraints that we'll talk in a few minutes. Okay, let's focus for a minute on the data term. There are choices for data target. Well, traditionally, all times, the least square target function was used to be used, and it's actually still used in small molecule crystallography. But today's almost all macromolecular packages use maximum likelihood target function, which is a little bit more scary function. So why maximum likelihood target function? What's good about it? As Paul and Tom already mentioned, the maximum likelihood target function has a better, more realistic error model, and also in protein crystallography we never have complete models. We're always missing. Sometimes we're missing side chains, sometimes we're missing alternative conformations. We never have full model for ordered solvent, and so on and so on. And so we always have incomplete models. So we always have a certain amount of scatters that are not included into our atomic models. And what's good about maximum likelihood target and formalism is that it allows to bring this missing information into refinement in some statistical way. It could be a separate lecture to describe how it does it, but just in a nutshell, so maximum likelihood target function accounts for missing a structure in a statistical way. So when you do refinement, it kind of thinks you have more or less complete model, even though you don't have all the items there. So, and this is for real space, reciprocal space refinement, but you may also hear about real space refinement, which conceptually same thing. We have certain target. We don't have maximum likelihood target for real space refinement, where it's basically the least squared difference between observed density and model calculated density. Well, there are some other more efficient calculation-wise targets that can be used. And traditionally, real space refinement has a long history, but is actually underused in general in refinement packages. And it's good that it's catching up and becomes more and more routine part of structure refinement tools. So in particular in Phenix.refine, we extensively use real space refinement tools. So what's good about real space refinement? Just fundamentally, so one very good thing is that it can be done locally. Imagine you refine huge ribosome structure. You change something. You don't want to refine the whole thing again. You can just do it in a little box around the area you're interested in. And you can do box by box. You can do locally, and that means very quickly. You can also do grid searches, which means you can extend convergence radius. For example, you can take side chain and just sample all chi angles. And again, that can be very, very fast and have huge convergence radius. So basically, things like this can be performed very quickly as part of real space refinement. That's why it's a very powerful complementary part.
Do you do this by hand or what?
No, it's done fully automatically as part of Phenix.refine. Yeah. Okay, let's spend a few slides talking about restraints. So why and what it is. So there are two types of restraints that we tend to call standard restraints and extra restraints. So why do we need restraints? Well, in protein crystallography, we deal with a variety of data qualities, translated into resolution from high to low resolution. So high resolution, we see atoms. So probably in a case like this, you don't really need restraints, or don't need sum of restraints, because atoms are well resolved. But as we go to low resolution, like here, or 3 angstrom resolution, well, here we kind of see the side chain shape, but we don't see individual atoms. If we inform some chemical knowledge onto this structure, atoms may just collapse somewhere, fill this bag of density in some random way, and that wouldn't make any chemical sense. That's why we need to bring some extra knowledge about chemistry into refinement, and that extra knowledge is called restraints. But traditionally, standard restraints include bonds, angles, dihedral polarity, non-bonded terms, chirality, and so on. So basically restraints on covalent bonds, covalent angles, restraints on torsion angles, non-bonded interactions, and so on and so on. And typically it's just a quadratic function where the model value with the difference of model value and current value. And model value typically derived from some a priori knowledge like QM calculations or databases of high resolution structures and so on. As we go to low resolution, it turns out that standard restraints are not sufficient. Indeed, say if we have 6 angstrom resolution map, well, it looks like a blob of density, and clearly we wouldn't see that helix here very nicely defined by the density. So if we do not apply extra restraints, then if we start defining this model against this map, the secondary structure will deteriorate very quickly as part of refinement. So refinement wouldn't really work. That's why it is important, working at low resolution, it is important to apply extra restraints. And those extra restraints can be a number of things. One is reference model restraint. So if you happen to have, if the structure you work on, low resolution structure you work on, happen to have a similar structure but solved at higher resolution, then that high-resolution structure may inform refinement of low-resolution structure as a reference, being used as a reference through restraints. Other tools can be explored, like secondary structure restraints, internal plot restraints, NCS restraints. If you have NCS copies, we can apply NCS restraints or constraints in refinement. So basically the idea is if you have low-resolution data or map, you need to bring all possible information you can come up with to make refinement actually practical and or meaningful. Okay, so moving on, optimization method. So once we know what are the model parameters and we know how we bring model parameters, how we relate model parameters to experimental data, we need a way to move model parameters in such a way that optimizes the target function, so we get improved model. And that's what it's about, optimization methods. And there's a broad varieties of optimization methods that are very schematically summarized here. So most of the time we use gradient-driven minimization. So this is, again, very schematically, we have target function profile. This is our starting model here. And well, the gradient-driven minimization is it's local minimization, and it's really cannot escape energetic barriers. So if you are here, chances are you end up here very, very good, and you'll never get across the energy barrier. So there are tools like simulated annealing, when you heat structure and then relax and cool. So that actually allows your structure to jump over minima and eventually end up in a deeper minima. And if you deal with refinement only a few parameters, like a solvent parameter, K-sol and B-sol, it's just a few parameters. You may not utilize very sophisticated machinery such as minimizers. You can just sample possible values in possible range, and it's what's called systematic or grid searches. And also moving your structure by hand and code is also refinement. It's also optimization. You optimize just by hand. You optimize your model into the data, which is map. So hands and eyes is also optimization tool in a sense. So yes, I touched on this already, but this illustrates, compares essentially different optimization methods, the convergence strategies and performance. So for example, if you have minimization and a situation like this, where side chain sticks out of density a little bit, well, minimization is likely to bring the side chain into density with no problems. If you have something like this, then it's very unlikely that minimization will be able to pull side chains into the density, while there's a great chance that simulated annealing actually will do that. And difficult case of something like this, it's very unlikely that minimization and simulated annealing will build into the density, while grid searches, these searches, systematic searches, samplings of chi-angles, will actually do the trick and put it into the density. Okay, now what I wanted also to mention is that in general, refinement is a local optimization method with rather small convergence radius, because the target function profile is very complex. So, and typically if we end up somewhere here and we do refinement, it's very unlikely to jump somewhere far away from here. We'll basically roll down closest minimum. So what that means that even slight changes in input structure might generate slightly different results in output refined structure. For example, we can take a structure and run 100 simulated annealing refinement runs with different random seeds. Everything is identical, just different random seeds. And in the end, what we are going to get are an ensemble of structures, like here, that are all essentially similar, but slightly different in details. And this illustrates a convolution of two effects. One is refinement artifacts. So it's basically, in one case, the model could converge into the local deeper minimum, and another one it could converge into less deeper minimum. It may also capture some functional structural features, but that would be difficult to deconvolute. So this kind of idea provides an uncertainty of R factors and refinement results. So this is why it's very good to keep in mind when you run multiple refinements with slightly different inputs and you get slightly different R factors, you need to keep this in mind, because the difference in R factors may be just due to the fact that your refinement took a different path to a slightly different minimum, not because you dramatically improved something or else.
So what's in the figure?
So that's the ensemble of structure result of 100 refinement runs. So there's 100 structures or so, and here the R factor for each one. So the R factors, you see, they oscillate within certain range, R work and R free.
No, I'm talking about this picture.
Is it different?
This one?
There's a spread, there's a
Yeah.
distribution.
So
Distribution comes from different instances of refinement. Oh.
yes. So each structure represents individual refinement run. Yes. And so the differences may have two sources: refinement artifacts, instabilities, and capturing something actually real.
But probably that region has bigger B factors and it's less well determined. And so
Yes.
the confirmation fell at a slightly different local minima in each case.
Exactly. Yes. That's
It doesn't mean that those are conformations that exist in the crystal.
true.
It just means they're accessible to refinement and fit the data. So it's okay.
Okay. Yeah. That's very true. Okay.
So how do you determine which is the correct structure?
Oh, it's
The region that is ill-defined.
it's just shows you an uncertainty. That means you probably wouldn't measure distance between these two atoms, because there's a flock of side chains. So the uncertainty is great. What is correct structure? Well, maybe all of them are correct. So
Shouldn't they be represented as an ensemble so I can mark
ideally, try to deposit that to PDB. You'll see why it's not done yet. But yeah, no, ideally that's the representation of uncertainty. And that's very simple way to access it. Just run a bunch of refinements, you get the picture. Okay. Anyways, for the sake of time, I keep going. So just a quick summary of what I just said. So what is refinement? Refinement is the process of changing model parameters to optimize your model so that it fits the data. We use various tricks to make this possible, including using various restraints depending on the context. Also, it's good to mention that refinement is one of the least automated steps in full structure determination process, meaning that you researchers need to make conscious decisions about certain things when you run refinement. That's why we have these workshops, so you learn what to do in different situations. And typically, garbage in, garbage out applies very well to refinement. So obviously, refinement is not getting low enough R factor to just satisfy your supervisor referee, or same for B factors. And it's not completing density and putting something into the void just because it's in the sequence, but you don't see it in the map. And finally, so basically the full story is described in a formal way with everything, equations, and many words behind. And in this kind of review paper published in 2010, where you can get all the information. It's available on the website. You can just download PDF right now. Okay, that's all about general introduction. So before I move forward, any questions so far about it? Okay, I'll move forward, but you have a chance to think about questions. I will repeat my prompt to ask questions again. Okay, next I'm going to talk about very relevant thing, Phenix.refine, where all these ideas, fundamental ideas about structure refinement are actually implemented in a Phenix refinement tool that is available to everyone who has Phenix. And I will briefly go through main aspects and ideas of Phenix.refine as a structure refinement tool in Phenix. So Phenix.refine is a tool for reciprocal space refinement, so against refinement against measured intensities or amplitudes. And first few slides are going to be statistics and numbers. Just so you know, you have choice of various refinement tools. Some of them are quite old, older than I am currently. So Shellax goes back to 70s, and Shellax L 1997. The Shellax L, the program adapted, Shellax adapted to macromolecules. RefMac is 1997. Explore CNS 87. TNT 87.2. I actually don't know for sure Buster TNT when was released. I presume it's 2000, but maybe I'm wrong. I wouldn't bet on that. That's what I quickly found. I mean, at least the first structure published by Buster TNT well on PDB is dated by year 2000. And another bit of statistics is here. So basically showing how many structures per year sold in Phenix and deposited into PDB since the birth of actual tools that people can use. So in 2006 it was just 7 structures, then 85, then it grows and keeps growing year after year. And now if we have another look at the numbers here. So here we are looking at the distribution deposited structures by different programs from 2010 to now, and from 2013 to now, and we can see the major 2 contributors are essentially RefMac and Phenix, and we improved as of very recent years. We have pretty much the same share of deposited structures. Which is nice. As I said, there are tools out there. So how Phenix.refine is different. So what's conceptually, technically different in Phenix.refine. And this slide that I keep showing over years illustrates the basic idea. So, well, this is an example from a paper I came across by accident, where people show how they refine structure in many various steps. So basically, starting from using CNS, doing rigid body refinement with simulated annealing, then switching to doing isotropic bifactor refinement, but then at some point switch to Shellax L and do an isotropic bifactor refinement and model hydrogens and so on and so on. So as you can imagine, it might be tedious because 2 programs have very different conceptions of input file formats, pretty much everything. So, and jumping between programs is error prone. So there's a good chance to make a mistake in file formats and then overlook it and then struggle for months with that error. So clearly with today's tools and software, we can do all the steps automatically. And that's essentially, that's the goal of Phenix.refine. So why don't we just do all the steps fully automatically as part of one refinement run? So that's the Phenix.refine philosophy. Okay, by means of just very brief overview, what Phenix.refine can do. Well, pretty much everything. So we cover a broad range of resolutions from low to ultra high. Ultra high is 0.5. So recently I refined a structure of 0.3 angstrom resolution for someone. We can do it in Phenix.refine too, but we can also refine against low resolution data with all these new restraints specifically designed for low resolution refinements. And we have various model parameterizations and various tools. I don't have time to go through each of them, but you can see you can do pretty much everything you want to do. So there are three ways to run Phenix.refine. So you can run it from the command line if you like to run things from the command line. So like, for example, I do run things from the command line. But I realize 90+% people use the GUI, which is great. Yes, you can use GUI to run Phenix.refine. We'll practice this tomorrow morning, first thing. And also, it's available as modules at Python scripting level. So, for example, if you're developing your own model building tool that requires refinement, you can import Phenix.refine and use it as refinement engine. This slide illustrates what happens when you run Phenix.refine. Basically, what happens is there are three stages. One is swallowing all inputs and digesting them, and then and I should say inputs can be any. It's very sophisticated about it. So, for example, you can give any reflection file format. It can be ShellX, CNS, CalePack, MTZ, any combination. For example, we can have amplitudes in ShellX file, R-reflex in MTZ file, Hendricks and Altman coefficients in ShellX file. You can give 3 files, and it will figure out all the sources of information, put them together, and it will know what to use in refinement. We also support a PDB file, model PDB file. We also support MMC files as model and reflection data too. So, and the green here part is what the main body of refinement we call refinement macrocycle. So this is where this is a repetitive block of events. That's where actual refinement happens. So just by design, it starts with bulk solvent modeling. Then we place ordered solvent, calculate target weights, do coordinate refinement, B-factor refinement, occupancy refinement. Then go back, update bulk solvent model, and do it in circles.
How do you define ordered solvent?
Ordered solvent is just water for now, but we can place various ions too if requested, like calcium. So that's not Eccles' work. So what typical way of doing it? You refine your model. You got to the point when you're ready to model waters, right? And what people usually do, go to Qt and start manually picking the waters. And as you can imagine, if you have a large structure, that might be a very tedious exercise, going just one by one. So Phenix.refine can do it for you in one refinement run. It will place all the waters, refine, update them, remove if necessary. Of course, it's a very good idea to check waters manually as a final step, which is a little bit of exercise, but it is nothing compared to doing the whole job by hand from scratch. So that's basically what it does. Right. Yeah, and by the end, it outputs files. It outputs TFOs minus of calc, residual map, anomalous difference map if you have anomalous data, and log files with lots of information. Just going to go very quickly through main highlights that I just arbitrarily picked. What's going on?
We may have to restart the.
Yeah. Haven't done anything.
There's a timer on the projector that it auditions.
I was noticing something red was blinking here.
Oh. Yeah, timed out.
Fantastic. Thank you so much. So just going to run quickly through highlights that I randomly picked that I think unique to Phenix.refine compared to other programs. So first of all, it's very flexible. This is a quite crazy example of what you can do in one refinement run. So you can refine rigid, for example, if you have something like this, you can define a rigid body and overall B factor for one part. You can do individual coordinates in TLS for another part. You can do individual coordinates, TLS, and restrained isotropic B factors for the other part. And on top of that, you can add water peaking, simulated annealing. You can use hydrogens. It can all be done in one refinement run, and you can totally flexible in selecting what you want to refine and how. So it's extremely flexible. The other part, I mentioned that already, so it builds waters automatically, which is a great help if you have big structures with lots of water. It's a good idea to get all the waters built as part of refinement, and once you are ready, have final structure, just check them by eye and make sure there are no spurious waters. We have very efficient rigid body algorithm that we implemented not so recently. When we did it? In 2009. So I still say it's recently, but time flies. So what's good about algorithm rigid body? So traditional way of doing rigid body, you basically need to cut the data resolution at some point. You don't want, if you have 1.5 angstrom resolution data, you don't want to use all reflections to do rigid body refinement. You want to cut them at somewhere like 3, 4, 5, and depending on where you cut, that will affect convergence radius of refinement. So basically, you never know where to cut. So it's a difficult problem. Basically, you solve it by trial and error. And we managed to automate the whole procedure the way that, so this is how it works. So we start with some number of lowest resolution reflections that we have algorithms to estimate it. And we do refinement against those lowest resolution reflections first. So that gives you the highest convergence radius because the map is featureless at that resolution. And then we gradually keep adding higher resolution reflections and keep refining the model. So this way we get highest convergence radius and highest accuracy of our final result. Of course, there are parameters are involved into this process, and we found optimal parameters by doing thousands of hundreds of thousands, hundred thousands of refinements on different modes just to find proper optimization. So rigid body refinement is very efficient in Phenix.refine, supposed to be. As I mentioned, we do have rotamer fitting as part of refinement. So basically, if you have something like this, Phenix.refine will automatically identify it and fit correctly into the density. If there are waters placed by mistake into sidechain density, that's not a problem because the sidechain will have a priority with respect to water. So waters will be kicked off as part of this fitting. So this is very fast. So the latest code, it used to be 6 seconds per residue, but just 2 weeks ago I moved all the code that does the calculations into C++, and all of a sudden it's 1 second per residue or less. So it's really optimized now. We have so-called NQH flips. So imagine a situation like this. If you don't have hydrogens, it's difficult to tell where the oxygen and nitrogens are. So basically, you can't differentiate between these two situations. But once you add hydrogens, all of a sudden you see favorable and disfavorable steric clashes. So, and by adding hydrogens, we decide how we need to flip the side chain so it makes favorable contacts. Again, that happens automatically by default as part of Phenix.refine run. Speaking of B-factor refinement, as I mentioned, did I? Yes. So atoms have in constant vibration, and the source of vibration come from different sources, actually. So atoms move by itself. They move as part of group motions. For example, sidechain may undergo some motion. Then that motion may be convoluted with the bigger part, domain motion, whole molecule motion. So it's a hierarchy of motions that contributes to the total atomic vibration. Basically what is outlined here. And the way we parameterize it in Phenix.refine is exactly this. So we have basically the total B factor that comes into calculation, atomic B factor. It has several contributions. One contribution is the local vibration, then group vibration, which is typically come from TLS or group B factor refinement, and the overall crystal vibration, which is accounted for as overall anisotropic scaling. And that actually very powerful thing to model atomic displacement as illustrated here. This is just an example of 3.2 angstrom resolution structure taken from PDB code 1DQV. Published R factors 2934. If we just do Phenix refinement with isotropic restraints B factors, the B factors drop quite significantly. But if we apply this hierarchical combination of parameters on atomic displacement parameters, we can reduce R factors pretty much by 9% essentially. So this really matters. And that's not unique example. You can find many examples that would behave like this in PDB. Of course, when we deal with TLS, next question arises: how you define TLS groups? It may not be a very straightforward way. So in Phenix, we have a very quick way of identifying TLS groups. It's built into the GUI. I will demonstrate this tomorrow morning. And it's very fast. We implemented very fast algorithm for TLS identification in Phenix.refine. So there's an alternative method of identifying TLS groups done by Ethan Merritt called TLSMD, I think.
Excuse me, what does it stand for? TLS?
TLS is translation, libration, screw, rotation, motion. It's basically it's a way to describe a rigid body motion of a macromolecule or domain or group of atoms. It's concerted motion, and a way to translate it into B factors. So you can think of it as constrained anisotropic B factor refinement. That's another way of thinking about it.
It's a matrix description of some motions that are sort of, but not exactly like rotations, translations, and screw-like motions.
Yes, yes. So there is a publication available at Phenix webpage. It's about 50 or 60 pages of very comprehensive review, going from very basics to deriving all the formulas. Very thorough. So if you really want to learn that, it may be worth reading.
So that's applied to the entire area, and that's just
Whatever group you want.
Mm-hmm.
Oh.
Yes, true. So as I said, we have built-in tool in Phenix to define TLS groups, very quick and efficient. And this is just to compare our approach of doing it with approach implemented by TLSMD. So this is GrowEL structure with so many residues, so many atoms, 7 chains. And we can do it in Phenix in about slightly more than 2 minutes using 1 CPU and 44 seconds on 10 CPUs. And similar job using TLSMD server will take way longer. And that is just another example. So what we have is pretty much interactive. So you can launch it into the GUI. In the GUI, wait a few seconds, and you'll see your TLS groups. You can explore them and try to make sense of. Okay, finally, occupancy refinement. So it's very comprehensive in Phenix in the sense that we can have all kinds of crazy things defining occupancies. So one is the simplest way. So you have 2 side chains and alternative conformations. That's the easiest case. We can do it. More complex could be having different chemical items sharing the same place at partial occupancies. That is possible to do too. We can define group occupancy of ligands. What else? Well, specific to neutron crystallography, we can have hydrogens and deuteriums sharing the same place, and the occupancies will be constrained. So and that's not limited to this. So there are many more situations that you can explore with occupancy refinement. So we have, as I mentioned, it's a good idea to refine, to use low resolution restraints designed for low resolution. We have all these restraints in Phenix.refine available. So NCS restraints and constraints now, secondary structure restraints, reference model restraints, it's all available. You can use it right now. And I think that's the end of this part. This is the slide that I always show, even though Paul and Tom showed it already, because that's one of the important slides. So if you use any of these tools and you encounter a problem, it's very important that you report it to us. I mean, it's important for you because we can solve it. We can solve this problem for you. And it's important for us because we improve software. So typically when we solve a problem, we make a test case for this particular situation, making sure that the specific problem will never reappear again. And so it's mutual benefit if we do it this way. So what's important is to properly report the problem. So I get heaps of emails saying, hey, something crashed and please help me. So there's no way for me to know what crashed and how I can help. So best way is to send actually all the data that are necessary to reproduce particular problem and instructions, what I need to do, what I need to click or run so that I can reproduce the problem. And then I will do my best to reproduce the problem. Maybe I will go back to you and discuss things. And if problem fixed, I'll tell you it's fixed, and next nightly build you'll have a fixed version of Phenix. So it's supposed to be very interactive, and it's very helpful for both sides. Okay, any questions about this part? Thank you. So if no questions about this part, then the last part that I'm going to spend less than 20 minutes. We'll try. I don't know if I run out of time, how badly I run out of time.
Well, we can go a little over, right? But technically, we're supposed to go until 4:45, but probably 5 o'clock is okay, or 5 is okay. Yeah.
I mean, I will not spend more than 20 minutes, even less. So.
Yeah, I can try and do the validation real quickly as well. Okay. So, yeah, can you do 15?
15, yeah, I will try.
I can do the validation.
I have many examples that I can skip. So let's do it.
So are there examples which fails? I mean, what this always works or what? I mean, what? Are there
Sorry.
problems or cases in which this is leading to nowhere or getting worse after the refinement?
Well, every time this happens, we are very interested to know why this happens. So if you experience exactly this situation, you run refinement and things get worse, then I would greatly appreciate if you come to me and explain the problem, and I will try to investigate and find what is going wrong, and eventually we may solve the problem. So no, it's definitely, it may happen for whatever reason that something didn't work as expected, or there's a bug, or there's just fundamental limitation of the tool. So it's well possible, but it's very good to know that us developers know about this.
In my experience,
Maybe you didn't choose the right strategy to refine.
in my experience, when it doesn't work, where it doesn't work is defined as the structure didn't get any better. It's usually because of some misunderstood disorder or problematic pathology related to the general solution.
Yes. So every time something goes badly, it's almost likely, it's very likely that the data.
Wrong space group.
Yes,
or
exactly.
Some disordered subunit or something.
Some pathology with early stages.
It's not your problem. It's the user's problem.
Well, that's easy for me to say.
Well, if the R factor gets worse, it's probably a bug. If it doesn't get better,
Right. So yeah, our factor shouldn't go worse. If it does get worse, then it's
so it shouldn't get much worse.
then it's worrying. Okay. So that's the final topic for today. I'll briefly describe. This is very recent tool. This is something I've been working last several weeks, and I'm still working. So I've made recent changes just last night. So it's very dynamically developing tools. So basically I'll describe real space refinement tools for refinement atomic models into cryo-EM maps and low resolution crystallography maps. So sounds like we get more and more cryo-EM structures, and due to technology advances and so on. So this is just show the statistics, how many structures we have in PDB at present, and this is just a share by year. So I get more and more structures, and just recently I had this very high resolution cryo-EM structures published, not very recently, and they basically approach lowish or medium resolution X-ray structures, and this is the distribution of cryo-EM structures, resolution of cryo-EM structures in PDB. So you can see there's about 50 structures around 3 and 4 angstrom resolution, 15 or so, 5, 6, and so on. Of course, there are a bunch of very low resolution structures. So basically, the development of these tools is kind of user request driven development. So I didn't, back in 2013, I didn't really plan to work on this that closely. But then people started coming to me and saying, "Oh, I've got cryo-EM map and model. Can we refine it in Phenix?" That's very typical question that I got from the people asking over and over the same question. And the answer was, well, kind of. And why the answer is not so brave is because we can repurpose existing crystallographic structures, existing crystallographic refinement tools to kind of thing they want. Well, take cryo-EM map, convert it into structure factors, convert phases into Henderson-Lantern coefficients, and then we can use MLHL target function for conventional crystallographic refinement. And so then from that point on, we forget about map and we do refinement. Well, if you think about it, clearly it's not the most optimal way of doing it, although valid way of doing it and possible way of doing it, but not most logical way of doing it, because, well, you have a map, and map is your primary source of data. So why not just take model and feed it into the map rather than take a detour through reciprocal space and use tools that are not really designed for dealing with cryo-EM specifics. So, and that's kind of approach we adopted as a main strategy, development strategy in real space refinement in Phenix. And we wrote in around 2013, we wrote a tool called Phenix Real Space Refine, where we outlined, basically documented the current state of the art and documented our vision and future plans about the future development of the tool. And since then, we made significant progress improving this tool, making it as of now ready to use by the community. And it still changed very rapidly. So if people use it and run into any problems or have wish lists, I would greatly appreciate if you send it to me, as I will implement them right away, because that's kind of area I'm very actively working on right now. So just wanted to outline challenges and observations that I found when I was working about it. So basically, my approach was, okay, I wrote that tool, can refine models into maps, but then I started looking into cryo-EM structures in database like PDB, MDB. And one shocking observation was that these structures are not very good geometrically. So, for example, here, looking at all CryoEM structures in PDB, we have, so in 30% of PDB models, we have 10% of Rotomy outliers. And 10% of PDB models have more than 20% of Rotomy outliers. And don't forget, we are talking about very low resolution. These maps will not justify any Rotomy outliers. So the goal here is to have 0. Same bad situations with Raman channel plot outliers. We have 5% of Raman channel plot outliers in 90% of models in PDB. We have more than 10% of outliers in 35% of models in PDB. Again, we all know that outlier, Raman channel or Rotomy outlier is not a bad thing. It may be a valid outlier if and only if justified by the experimental data, by the map, for example. But we are talking about, again, we're talking about very low resolution structures where those kind of details are not really visible. So this is one challenge that I faced right away. The other challenge is size. So Phenix.refine was just chalked on this model because it's just too big, right? It's a million of atoms. Then resolution. So resolution can vary. I mean, it can vary from 2.93, very nice, but it can also be like 10 angstrom resolution, and might be very difficult to refine. Another shocking experience that maps may be great, but may be very poor, and which are very challenging to move model into it. So having that those observations, that basically made us to formulate the set of goals for Phenix Real Space Refine. So what we really want to do as the strategic plan for development. So we want Phenix Refine to provide best model to map fit under the constraint that there is no geometrical outliers. So structures are chemically correct, chemically and physically correct, and fit the map as good as possible. Also, we don't really want to focus on and limit ourselves on cryo-EM maps. So we say we can refine against any map, neutron scattering map, X-ray map, cryo-EM map, whatever map you give us. So it's not important which map we use, because intrinsically all the protocols, they do not rely on map type. Map for all the protocols, map is just a mathematical object. It's totally abstracted away from its identity. So it needs to be fast, because again, when I run Phenix.refine on a big structure, it took several days. So, but the goal is to have it fast, seconds, minutes, maybe hours, in very big cases. So we want to have large convergence radius, because I've seen structures from users that are very, very distorted. So in some cases, you need to move the entire helix arrangement of helices or beta sheets distance away before they fit electron density. So it needs to have large convergence radius. And as usual in Phenix, we try to make tools that are easy to use. So in this particular case, you can just run the tool by giving it a map in CCP4 format, or MTZ file with Fourier map coefficients and input model, and it will do refinement for you. So just briefly, this is how our whole refinement protocol looks like. Conceptually very similar to Phenix.refine, but has specifics to real space refinement. Again, we have input model. We can do rigid body refinement. We can idealize model if model is very distorted. We can do Tom Terwilliger's morphing. We calculate weights between map term and geometry term in a very, very efficient way. We have specific algorithm to do it in a matter of seconds. Don't have time to describe it now. We can do geometry. We can do minimization, gradient-driven minimization. We can use internal symmetry, what if present. So if you have like 60-fold virus or whatever, the NCS constraints will be used properly during refinement. And yeah, we can use simulated annealing. We can fit rotamers to rigid body, do it in cycles and so on. So, and just finish the several, I'll show a few examples. So this is kind of showing performance of the tool. This is start model before refinement, very bad map. And this is what Phenix.refine is actually able to do. Just another example. So we have something here, but it can move atoms into poor map distance away from starting point, which is good. And then I have a few randomly selected structures from PDB. So I didn't really spend any time selecting them for whatever reason. So I just picked some of them. So basically what we have here, we have so many residues, so many atoms. Refinement took 20 minutes. It's not a long time. So we improved correlation coefficient from 65 to 71. Clash score went significantly down from 100 to 33. We don't have Ramachandran outliers. There was a large amount of rotamer outliers, so all these guys went to 0 as expected. Another example took 15 minutes to refine. This is a rather small example. Again, we improved from 0.596 to 733 map correlation coefficient. At the same time, we improved overall covalent geometry. We improved significantly clash score, got rid of most of Ramachandran outliers, no rotamer outliers, C-beta deviations were improved too. Another example, this is very dramatic case where there's 600 C-beta deviations and lots of rotamer outliers, Ramachandran plot outliers, and so on, and so on. So we managed to get rid of all of these outliers, so the structure makes chemical sense at the expense of just a slight decrease of the model-to-map correlation, which is, I would say, is justified given that we make structure more chemically meaningful.
Move on from that one. So how do you distinguish, so your correlation has gone down and you strictly enforce the C-beta deviation. So how do you distinguish the C-beta going to 0 because you improve the model from you overfit in some way? I mean, we know the C-beta should be 0 deviation, but how do you know that you haven't overfit more in some other way compared to the original model in this case? Because you have no R3 to look at.
Well, it's a very good question. There is no R3, but basically you need to choose. Here we have a binary choice. You have a marginally larger map correlation and hugely distorted chemically hugely distorted structure. That's your first choice. And the second choice, you can get rid of all chemical nonsense from your structure at the expense of slightly lower map-to-model correlation. So personally, I would choose the second option, but that brings a good question about cross-validation and necessity of cross-validation and so on. Yes? Yes, what?
Have you tried to calculate the Fourier shell correlation between the map and the model after the Phenix?
It actually calculates. I don't have it here, and I don't remember how it looked like in this particular case. But it's part of input of the procedure. So unfortunately, I don't have it right now with me. But yeah,
Presumably it's being improved.
I hope so. Yeah. Yeah. No, that's the good. That's definitely the good. It's among of the inputs. Just didn't have place to show that graph here. Yes.
And I think while I use the right term, this procedure is an optimization. It's not refinement unless you actually produce a new map from that and then do this again.
Yeah, it is optimization. So.
It is an optimization, yes.
Yes.
To call, yeah, and that's sort of.
So you don't produce new map because your map is static. Yes.
I think that would make
So far.
use of terminology though. I mean, when we say refinement, we mean optimizing a model against data. It's nothing to do with making a map or doing a new
But
reconstruction.
intrinsic to refinement is cycling through those new maps.
But it doesn't have to be iterative
Doesn't have to be.
refinement. So
Doesn't
you
have
have
to
to.
be.
That's fine.
Your terminology is iterative,
not
right?
confused, that's fine.
We're not confused.
Because somebody's not going to be confused when you use the term refinement, you mean you improve your method.
Yeah.
But if you guys are happy with it,
That's the way we use it. It's
I know
not.
that's the way you use it, but usually the software expect
A
that
new
you
map.
also a new map as well.
Yeah, but it was clear we don't make new maps.
No, we did our map, but
Yeah.
it's just a better terminology whether you want to adopt the term optimization at this point.
Yeah. What,
In the future, we will
It'll
change.
become refinement.
Right. Well, this is like the bad old days when people argued about how good should the geometry be versus how low should the R factor be, right? And then they gain cross-validation. So you guys fitting against different maps is the equivalent of cross-validation. So if you've got multiple maps and you leave one out and you fit the others, then I think that's going to be the equivalent to free R.
yeah. Right. Yes. Anyway. So just last example. Just one more. We improve correlation, get rid of outliers, so things look good here. To get more information, that's the last slide here. So this is Phenix documentation webpage, and at the bottom here we have Phenix documentation for electron microscopy, structure refinement. If you still want to do the old way, there are tools to convert map into structure factors and then use reciprocal space refinement tools like Phenix.refine to refine. So there's a tool here to do that. Also, some people find it convenient to, if you have something big, you probably want to refine piece of structure in a box instead of handling the huge molecule. So we have tools to extract box with map and molecule in it out of big structure, and then refine structure in that box, and then put it back into your initial model. So these are tools. I keep adding stuff here. So if you notice something missing or you have any wish list, let me know. I'll update that. And so yeah, I think I'm done with this part. Just to mention, we're thinking of doing next steps. We're thinking of working with Sasha or Junsif on defining standard way of CryoEM map resolutions. So how you calculate resolution of CryoEM map. We have some ideas. Well, I will voice them once we are ready to show something. So this is something we are working very actively. Hopefully soon we'll have something interesting to show. And second future direction that we are kind of brainstorming right now is I'd like to apply density modification techniques to CryoEM maps. This is something going to be very new, and again, we have ideas how to do it. We just need to try and see how it works. Of course, it will not work from the beginning, but we hope it will eventually. I think that's all for me. So, any questions? Otherwise, I'm still around. I'll be giving demo presentations in the morning. So, bring your questions. You don't have any now. Okay.